Welcome everyone. For today's prep, we're going to look at an example for how to graph polar curves. So the polar curve in question here is r equal to 3 cosine theta. So essentially what we're trying to do when we're graphing polar curves is we're trying to graph all of the points in the plane that have a polar coordinate representation that satisfies this equation. So we're trying to graph the collection of points in the plane whose polar coordinates satisfy this equation. All right. And to help with this, I have our polar grid drawn out. So this is the plane where we're going to be drawing our polar curve. And when we think of this plane, we kind of want to, again, we want to think of polar coordinates as being layers. So we have our kind of our plane, which is the underlying points. Then we're laying down our polar grid. And then we have our rectangular grid that we can kind of put on top of that. So when we think of this plane, we're going to think of x and y as being our rectangular coordinates. And we're going to think of r and theta as our polar coordinates. Kind of what we've been doing. So here on this plane, x and y are the rectangular coordinates, and r and theta are our polar coordinates. Well, to help with this, we want to graph this equation. We want to graph all the points that satisfy this equation on this plane where we're treating x and y as the rectangular coordinates. Well, to help with this, we're going to kind of introduce another plane. And let's kind of draw this out. So here's another plane, kind of in a separate universe off to the side here. And on this plane, we're going to make r and theta, whoops, wrong order there. We're going to make r and theta our rectangular coordinates. So this is a separate plane. Basically, this over here is a different universe of points. And over here, r and theta, we're going to treat them like regular rectangular coordinates. So we have our main polar grid over here, the plane where we're actually going to draw our polar curve. And this is where we're treating r and theta as polar coordinates. But to help us do this, we're going to first graph this equation where we treat r and theta just as regular rectangular coordinates. So we want to do this off in a separate universe, separate plane off to the side here. All right, so let's look at what this, if we're kind of just using regular rectangular coordinates here, what would this equation look like? Well, the cosine curve, we have cosine theta with this 3 in front. So the regular cosine theta curve looks something like this. And actually, it's important. Cosine goes through one full cycle in between 0 and 2 pi. So let's list some of the important angles for cosine. So pi over 2, pi, 3 pi over 2, 2 pi, and 0. All right. So that'll give us a good idea of what the cosine graph looks like. So cosine starts at its high point, and then at pi it hits its low point, and then at 2 pi it's back to where it started, back to its high point. And then at pi over 2 and 3 pi over 2, that's where it crosses the horizontal axis. So our cosine graph looks something like this. Okay, and it gets one full cycle from 0 to 2 pi. Now, all this 3 does is it kind of just stretches it out vertically. So when we have this constant multiple in front, it just stretches the graph out vertically. So normally cosine, its high point happens at 1 and its low point happens at -1. But now it's going to be happening at 3 and -3. So we're just stretching it out by a factor of 3 here. All right. So we have this equation graphed in regular rectangular coordinates. And we're going to use this graph to help us actually graph the polar curve. So let's start by looking at this section of our theta values. So we're going from 0 to pi over 2. And let's start with 0. So what this says, if we read the graph, when theta is 0, the R value is 3. So now let's go over to our polar grid over here. And, well, let's first just label some of these important theta values. Let's label the rays. So 0 is the positive x-axis, pi over 2 is the positive y-axis, pi is the negative x-axis, 3 pi over 2 is down here, and then 2 pi is back to where we started. All right. So when we're looking at this section of theta values going from 0 to pi over 2, what we're really doing is we're looking at the first quadrant. So we're going from theta of 0, and we're going all the way to pi over 2 here. And if we look at the values, all these R values here are positive. So specifically at 0, the R value is 3. So let's plot the point. So we find the 0 ray, and we count 3 units away from the origin. So this is going to be a point on our curve, on our polar curve. So that's 1 point on our curve. And what happens is as these theta values get closer to pi over 2, the R values are shrinking until we actually get right to pi over 2. And at that point, the R value is 0. So whenever R is 0, that means we're at the origin. So our curve is going to be at the origin at pi over 2. All right, so what's going to happen? How do we get from this point to this point? Well, we want to imagine we have this kind of directed ray that's extending out of the origin, and this is going to kind of trace out our polar curve. So what happens is when theta is 0, we have this ray, and it's 3 units away. It has a length of 3. And what happens is as we rotate counterclockwise, going from 0 to pi over 2, the length of this ray is going to shrink down, and it's going to shrink down to 0. So we start here on theta equals 0. It has a length of 3. And then as we trace this out, as we rotate counterclockwise, this is going to shrink down to nothing. So let's graph what this looks like. So if we graph we're going to get something, yeah. And as we'll see in class, it's going to be the top half of a circle, actually. So we get something like this. So again, just to kind of see, as we're going from 0 to pi over 2, we want to imagine almost kind of like radar. We have this directed ray extending out from the origin. It has a finite length given by our kind of our separate plane over there. And we're going to rotate this counterclockwise. And as we trace out that curve, the length of that little line segment shrinks down to nothing when we get to pi over 2. All right, so now what happens with the next section here? So going from pi over 2 to pi. Well, on this section, this is the second quadrant. So we'd be graphing over here. So we're going to graph our curve over here. But if we look at our kind of separate view here, all of the R values are negative. So normally we'd be graphing things in the second quadrant, but because the R values are negative, we're actually going to be graphing them down into the fourth quadrant, kind of the reflection through the origin, the quadrant that's reflected through the origin. And so what happens is as we go from pi over 2 to pi, our R value is going to start at 0, so we're going to still be at the origin. And then we're going to move away until we get to, on the pi ray, we're going to be 3 units away, but kind of going in the opposite direction. So normally if we're going to graph a point on the pi ray, we'd be graphing over here. But because the R value is -3, we're going to count 3 units back. So what happens is at pi, we're back to where we started. So we're going to get and because everything is symmetric here, we're going to get the bottom half of our circle. And so again, you want to think of it as there's this directed line segment kind of from the origin extending out to the curve. And as we rotate, it the end point of that line segment traces out the actual curve. Now, once we get to pi, we're back to where we started. So the rest of this is actually just going to retrace our steps. Now that doesn't always happen, but for this particular example we do. So going from pi to 3 pi over 2, normally we'd be graphing that in the third quadrant. But again, the R values here are negative, so we're going to the polar opposite region of our plane. So we're going to be graphing in the first quadrant. So we're just going to retrace our steps. And then when we graph from 3 pi over 2 to 2 pi, well, now that's in the fourth quadrant here. And there we do actually graph. So if we were to kind of watch the action here, we have our little radar screen, and we're going to rotate counterclockwise around the origin. And as we do, our line segment starts here, and then when we go from 0 to pi over 2, that line segment shrinks to nothing. And then from pi over 2 to pi, the line segment grows, but it's in the opposite quadrant. And then from pi to 3 pi over 2, the line segment shrinks back down to 0, but again, we're back in the opposite quadrant. And then from 3 pi over 2 to 2 pi, we're just kind of tracing it out in the fourth quadrant where we should be. So essentially, we're going around that circle twice. We trace out the circle twice. So this, ultimately, is our polar curve. So we ended up with a circle. Now, we'll see in class. We'll look at this example in class, and we'll figure out the Cartesian equation in terms of x and y, and actually confirm that this is a circle. But for right now, just getting a little exposure to see how we're going to graph these. So it's kind of a two-step process. We first want to plot what this curve looks like on a separate plane where we're treating r and theta as just regular rectangular coordinates. And then we're going to graph them on our polar grid where we're treating r and theta as polar coordinates. And that's what gives us our polar curve. All right. So we'll try a few more of these in class, but they're kind of fun. We'll see you then.